Alright. So, I am once again delayed in making a more formal presentation on entropy because it's a more complicated project than I really know how to do at the moment. So I'm learning how to do more complex projects. The closest thing I have so far is my psychrometrics video, which gave me at least some of the technical skills, but I'm still working on the sort of writing, composition, and sort of, well, I know how to talk to a camera, but talking to a camera through, an entire hour's almost worth of contents, and also how to make that content perhaps a bit briefer, because I am not usually reading from a script, and right now, of course, I'm not reading from a script, but for the entropy video, I'm going to have to actually write a script, and I probably won't stick to it line for line, but I'm going to have to do quite a bit better than I have in the past, so. Yeah. So, where's my little Stirling engine? That's a problem. I don't have that ready. So, I guess we're live, so I can't fix it, but it's also not that big a deal. So, maybe it's for the best I don't have the engine, because I tend to get... It's better to... yeah. So, really what I want to do is, in the broader video, connect two things. One, I want to connect microphysics to macrophysics. And two, I want to explain why the inverted form of the Boltzmann equation is so useful, right? So we're going to connect two things, which are the macroscopic definition of entropy, which is that delta S is equal to Q over T, right? Change in entropy is equal to heat transfer divided by temperature. Oh, hopefully it's hopefully it's not broadcasting inverted, hopefully it's just showing me the inverted version so that it's easier for me to look at it, because so the writing will be backwards. So, but we want to connect that to the definition of entropy in terms of microstates per macrostate, right? That's what W is W is microstates per macrostate, right? So for a given macrostate, which is, temperature, pressure, things like that, actual thermodynamic variables, how many ways can the atoms and molecules that actually make up that system arrange themselves? And it's not immediately obvious how that connects to this other definition of heat transfer divided by temperature. It does ultimately make sense when you go through things in detail, though. And the reason is that energy unlocks possible configurations of a system, right? Which, probably the simplest way to think about that, right, is if you have an ideal gas, which consists of a bunch of atoms and molecules all plinking around and bouncing inside of some volume, they are going to have some distribution of velocities, right? So if you have, it's actually skewed, but so if you have a distribution of velocities that looks like this, yeah, so these are not pressure and volume. These are, vertical axis here is probability of a state, and the horizontal axis is the velocity of that state, right? If you have some distribution like this is constrained by the energy, right? It technically goes all the way off here, but right, the average energy is here. You can see that this is, distribution has some width to it, and that width is characteristics of the number of microstates that can make up that macrostate. But let me get another color out here. Let's do purple. If we increase the average energy and make the distribution wider, right, you can imagine something like this purple distribution here. That has a much wider distribution, right? So there's a lot more possible microstates, and it has a much larger average energy, right? And that's where we get to something that's it's not a dodgy assumption per se, but any reasonable system, when you add more energy to it, it's going to open up more possible configurations of the system, right? It's going to make it so that there are more possible microstates. Now, that's technically not always a guarantee, right? You can reach a point where a system saturates on energy, and at that point, adding more energy will actually decrease the number of possible configurations of the system. But for something like the velocity of atoms and molecules inside of some volume, you'll never saturate, right? Because, the velocity can't go to infinity, but it can go to the speed of light, right? And so the momentum can go to infinity as it approaches the speed of light. And you can just open up more and more and more possibilities. To be sort of philosophically correct, though, I have to include possibilities like lasers. Oh, that's the blue laser. That's a little bit temperamental. Let me find the red one. Oh, it's the green one. I have a red, a green, and a blue. The red is by far the most reliable. Oh, there we go. Hopefully the cat doesn't pop up and change. Yeah, there we go. A laser here. So lasers rely on something called population inversion. So inside the laser pointer, there's actually more electrons in an excited state than there are in the ground state. And so once you have a situation like that, then adding more energy will actually decrease the number of possible states of the system. But that's, well, it's actually not getting too far outside of, like, the ideas we're considering here, because this brings up something that I'm always trying to explain, which is something called the zeroth law of thermodynamics. Because I will say thermodynamics is a set of approximations that only kind of makes sense. And the zeroth law of thermodynamics says that any two systems in thermal equilibrium with a third system are in thermal equilibrium with each other, right? So if I have, say, the blue pen and the red pen, or blue pen and the red pen, and I say both the blue pen and the red pen are at the same temperature as the green pen, then they're going to be at the same temperature as each other, which seems like a perfectly reasonable statement, and in fact it doesn't even seem like it requires a law of thermodynamics. But it requires that you assume there's such a thing as thermal equilibrium in the first place. And that's honestly a little bit questionable. It turns out to be a good approximation to consider things in equilibrium, but nothing's ever really in equilibrium except for arguably the heat death of the universe, and it's debatable if that will ever really happen. So, now with all that being said, if we consider sort of a well-behaved system like this, where when we add more energy, it increases the number of macrostates that are number of microstates that are possible, then we can reasonably say that adding energy to a system will always increase the entropy, right? Again, there's weird systems like lasers where you have population inversion, and adding more energy will not increase the entropy, but any system that is in thermal equilibrium will always have the entropy increase when you increase the energy. And that's not a law of thermodynamics per se, but it's implicitly encoded in the zeroth law of thermodynamics. So that brings me to trying to connect these two definitions, right? So in order to do that, we have to think, what is the actual heat transfer, right? So heat transfer is energy that is transferred via heat, right? And we have to consider the first law of thermodynamics, right? And the first law of thermodynamics says that the change in the internal energy of a system is equal to the heat transfer into the system minus the work done by the system. And that means that basically the internal energy and the entropy are linked, but they are not necessarily linearly proportional, right? Because you can have energy transfer without actually increasing the entropy if you do work on the system. So that's where things get a little bit complicated, because if you compress a system, you are adding energy to it, but you're not changing the entropy. But if you simultaneously, if you do isothermal compression or expansion, right, constant temperature compression or expansion, if you let a gas expand, or if you compress a gas, and you simultaneously transfer heat in and out such that the temperature is constant, the entropy changes, but the temperature doesn't. And that begs the question then, well, what is temperature? And that's the thing, right? Is temperature is not just a measure of how much energy is in a system. Temperature is actually a measure of how much entropy do you get for a given amount of energy that you add to the system via heat transfer, right? And that basically actually follows from this macroscopic definition, right? If you just rearrange this equation, right, you instead get that, T is equal to Q divided by delta S, right? So it's in some sense it's the inverse of temperature that maybe makes more sense, but a system that's hot is a system where you need to add, with a high temperature, it's a system where you need to add a lot of heat to get just a small increase in entropy. Versus a system that's cold is a system where if you add, just a small amount of heat, you'll get a relatively large amount of entropy for it. So how does that then let you connect to this other definition of entropy? Well, if you consider how the number of microstates changes with energy, right? Because we have the Boltzmann constant times the log of microstates per macrostate. And we know that the number of microstates is a function of the energy. And that gives the result that the amount of energy you need is proportional to something, right? So we basically want to say partial S partial Q is equal to partial Q, which this is playing very fast and loose because you can't technically you can't take the partial derivative with respect to Q because Q is not a state variable, but we're playing very fast and loose with things. So partial derivative with respect to heat transfer of K ln W, which is, for all intents and purposes, equal to partial derivative, again playing fast and loose, with respect to internal energy, or with respect to energy, of KB ln W, right? And if you remember how to take the derivative of the logarithm, derivative of logarithm is 1 over the argument, right? So then that in turn is equal to partial W partial U times KB times 1 over W. And that actually gives us back the result we want, right? Because partial W partial U, that is 1 over the temperature. And then the Boltzmann constant divided by the microstates, that basically is the 1 over the energy. So we're kind of back with what we wanted. Again, playing very fast, very loose with everything. But that's the massively simplified version. Yeah, I can put together some proper notes that'll explain it better. So, yeah.